So let's look now at how do we do the analysis if we have independent samples. Um, and so again, independent samples are where the one sample values do not have effect on any of the values in the other sample. So let's see, how do we analyze this when this happens? And so you're going to do the same as always. You can have a hypothesis test or you can have a confidence interval. The process is exactly the same no matter which one you use. The assumptions are the same for hypothesis test or confidence intervals. The difference here is that with a two sample independent test, you have different assumptions than you would for a one sample uh, test or proportion test. So we are going to look at whether we have a whole bunch of variables, usually in a data set. There's going to be quantitative variables that you want to make the decision about based on a factor that's usually a qualitative variable. And so you want to know if your variable of interest is different based on some qualitative variable. That's what we call the factor. As an example, you might want to know if drinking alcohol affects the pulse rate of individuals. The pulse rate would be that quantitative variable, and whether the person drinks alcohol would be the factor. For two sample t-tests, that qualitative variable can only have two values, such as yes and no. It can't have more than that. If your quantitative variable has more than that, sorry, if your qualitative variable has more than two, has more than two variables, then we have to do something called coefficient analysis of variation, or what we call an ANOVA. So we're going to look at just if we have just those two, so we can do the independent samples. Your steps are the same as every hypothesis test. You can use Mosaic as your package. Your hypothesis test is going to be you're going to look at you're going to start with your random variables and your parameters and words. You're going to have some random variable one. That's your measurements from what you considered your first sample. And then your random variable two would be the values for the variable for your second one. And that's going to be, you can have that factor going to be somewhere in those definitions. And you're going to mean for your random variable one and your mean for your random variable two is your parameters. These are what we want to find. They're unknown values. Then you're going to state your null and alternative hypothesis, just as before. You're going to look at the null is always that they equal. The alternative is that one's less than the other, or one's greater, or they're not equal, depending on what your question is that you're asking. So remember, the alternative hypothesis is based on your question. You can subtract these if you want to, so you can get them equal to 0, or less than 0, or greater than 0, or not equal to 0. If you want to, you always take mu1 minus mu2. If you want to, you can do that. It's a good idea to think of it. What you do not do is, like in a paired test, you don't call this mu sub d, because you aren't putting these together. They're not paired values. All right, you then state and check your assumptions. And your first assumption is that you have a random sample of a size n1 is taken from population 1, and a random sample of size n2 is taken from population 2. Realize they do not have to be the same size. You can actually have two different size samples. You can take one sample that's much larger than the other. It's better, and you have a more robust t-test if they are the same, but they don't have to be the same size. And sometimes that can happen where you have two different samples where you're collecting with somebody and somebody drops out of your study. So your sample sizes would change. We do know the second assumption is that these two samples are independent. That is the assumption we are making, or we can't be doing this type of test, this type of analysis. And then, as before, your population 1 is normally distributed and your population 2 is normally distributed. So we have these two. They both, one could be and one could not. You actually state these separately. They are separate assumptions. And then you would test them based off of each one's sample for each one separate. You're going to have a fairly robust, though, if the samples are large enough. If these aren't true, then it's okay. It's not really okay, but it's okay. It will work. Your test will still be valid. Then we get to our calculations. Again, these are all done with technology. You do not want to go through these formulas. We are using something called the Welsh Satterthwaite equation for the degrees of freedom. There are different degrees of freedom. If you actually have another assumption that the variances are equal, you have a different size of your degrees of freedom, but your formula is a lot different, a lot worse to work with. So this degrees of freedom formula is not very nice to work with, but again, we're gonna let technology do that for us. So on R, you're gonna actually put in your t-test. This is a little different. You're gonna have your variable separated based on that factor, whatever that factor was you're working with. And then again, you do alternative equals less or greater, depending on if it's what your HA is. Your conclusion and then your interpretation, just as before. Your confidence interval, same thing. You would have a confidence interval where you're looking for the difference in means. You want to know how much more is one over the other, how much less is one over the other. Those are the questions you might be asking. And so you'd be looking at that. And you again would state your random variables. You'd have the same assumptions as the hypothesis test. Your calculations are done very, very similar. And then you'd have your statistical interpretation and real world interpretation. And then you check your assumptions for your t-test. Again, you would state, how did you take your samples? How did you make sure that they were both random samples? And they both have to be two separate random samples. So you take a random sample from the first one, you'd randomly pick your units of observation to be in this sample, and then you do the exact same thing for this one. So you want to randomly collect for both of them. They are not going to be the same values. Then you'd say, how do you describe how they're independent samples? And then you'd look at each individual sample to see if they're normally distributed. So you'd look at your normal quantile plot and your density plot. And you do those two separately. So let's go ahead and do an example. And the question is, does smoking change a person's resting pulse rate? And we're going to ask that question and see if it does. We're going to use this pulse data set. So I'm going to go ahead and copy this and put this into R. And so here's my pulse data set. This is what that data set looks like. We have a whole bunch of units of observation. Each row is a unit of observation. They happen to contain the height, weight, age, gender, whether somebody smokes, whether they drink alcohol, whether they exercise, whether they ran or sat in this experiment, what their pulse rate was before and what their pulse rate was after, and what year this was collected. Okay, so now let's see. This contains those information. I already said that. The pulse before is before the exercise, and the pulse after was taken after the person exercised for 1 minute. We're going to consider a person's resting pulse rate. I don't care about their pulse rate after. That's not of interest to me. I want to just know, does smoking affect a person's resting pulse rate? So I don't care what's happening with the person's after. I'm only caring about that they're rested. And I want to see if smoking changes that pulse rate. So smoking changes that pulse rate. Going back to my data set, remember smoking was a quantitative variable, a qualitative variable. Categorical variable, that's a much better way to say it. A categorical variable that we had in here. We had yeses, we had nos, and that's all we have, yeses and nos. So we only have yeses and nos in that categorical variable. And so we know that smoking is my factor I'm working with. And then again, we're working with pulse before only. That's my quantitative because they're quantities, they're numbers. So we're looking at that information and we're going to use that information to figure this out. Okay, so we're going to test this at the 5% level, and I'm going to go ahead and show you all the different steps we go through. So again, your first step is to state the random variable and the parameter. So we have two. We have x1. I'm going to call it x1. You can call it anything you want. I'm going to call it x1, and that's going to be the resting pulse rate of people who do not smoke. And now I just said that, but let's go look at our data set really, really fast. Let me spell people correctly. I'm going to look at my data set really quickly here because that actually will make a little difference here. If I go to the very top of my data set, smoking, yes, came first. And what happens is R will actually consider smoking, the first one, whatever came first, is being your random variable 1. Secondly, put that as your first group, and the other ones as your second. So since yes is at the top of here, we actually want to call X1. You don't have to, you can call it anything you want, but just for ease of this, we're going to call this to people who do smoke because it just will be easier in our analysis using R. You can call it anything you want in normal places, but just for our sake, it's a little bit easier this way. So X2 is the pulse rate, the rest pulse rate of people who do not smoke. And I'll show you in a little bit why that was kind of important. You have mean 1. Your mean 1 is your mean pulse rate, resting pulse rate of people who do smoke. And then your mean 2 is your mean pulse, resting pulse rate of people who do not smoke. Okay. All right, so now our next step is to go ahead and do the assumptions. Well, let's do the hypothesis test first, the hypotheses. So we're going to state the hypotheses. Okay. Again, we have an HO and an HA. I prefer to do HA first. And my HA is, I want to ask if does it change? So I want to know, consider a person's resting pulse rate and use the data if smoking changes. So I'm only asking if it changes it. If I'm asking if it changes, then I'm actually looking at my HA would be the mean 1 is not the mean 2. That's all I want to know. They're not this, were they, if I want to know if it changes, I just want to know, are they not the same? And then my HO would be that they are the same. Okay. All right. Again, here you can also state your level of significance. Normally we figure this out looking at your consequences of a type 1 and type 2 error, so you have to write that out. But here in the problem, I did give it to you, so I'm going to say it's 5%. Okay, so now we can go ahead and state and check the assumptions. And my first assumption is a random sample. Well, now I don't know how many there are, so I don't know what the size is of my sample. I can come back over here to R and I can kind of figure it out. I could tally the smokes in the data set pulse. And it gives me an idea of how many there are. So there's 99 no's and 11 yeses. Okay, so they're not the same size. And again, that's okay. It's a little bit better if they were closer, but that's what we have. So a random sample of 90, let's go 11 pulse rates. And it is resting pulse rates of people who do smoke. It was taken. And a random sample. So this is a totally separate sentence of, and I can't remember the number I had there. It was 99 of 99 pulse rates, rest pulse rates of people who do not smoke was taken. So again, this is our stating part. So I like to put in the word start here. This is where I state it. Again, this is what's supposed to happen. This is what you're supposed to have happen. Doesn't mean it did. It's just what's supposed to happen. In this case, when I go to check it, I have no idea. So I don't know. I have no idea, so this assumption may not be true. The second assumption is that the samples are independent. And since I just kind of said what the samples were up here, I don't need to say them again down here. So again, this is my stating, this is what's supposed to happen. It may not happen, but it's what's supposed to happen. This one, if it doesn't happen, then you do a different analysis. So in this case, the rest parse rate of a person who smokes will not affect the rest pulse rate of a person who doesn't smoke. There's no reason why they would. So we have it. So the check is good. The third assumption, again, the stating part of it, is that the population of the resting, pulse rate of those who smoke is normally distributed. Again, that's what's supposed to happen. And then the other one is that the other statement is that the population of the rest pulse rate of those who do not smoke is not, who do not smoke is normally distributed. Okay, so now we go check that one. And again, we check that one using R. I'm going to do a normal quantile plot. I'm going to do a normal density plot. So we're going to come over here. I'm going to go ahead and do a GF density. And we can actually do these together, sort of. We can do pulse before. That's my variable. So make sure you get the exact name of the pulse of the variable. So you come up here and look in your data set. It's pulse before, just like I did with the underscore. And then we're going to do tilde that smokes. That way it'll separate based on smoking and not smoking. And then my data set again was pulse. And then you should have a title. The title should be something like the pulse rate, the rest pulse rate of individuals. And I don't need to say the other thing about them smoking or not smoking because that's going to be there. All right. Oh, that's right. It doesn't like that. So we're going to do the tilde first. And then instead of the tilde afterwards, we do a vertical bar, a vertical line. So that remember that vertical line is above the enter key. There's a vertical line, there's a slash and a vertical line. And there we have it. So there it is for no, not smoking, and yes, smoking. And they both look fairly nice and linear. I'm sorry, fairly bell-shaped. Not linear at all. Bell-shaped. So we're going to go back over here. I'll put in this command. And I don't need to do another command. I'll do the other one for the quantile plot, and then we'll bring both plots over. So we'll look at what the quantile plot looks like. Actually, it'll make this plot go away. So I'm going to go ahead and copy this to the clipboard, copy this image, and then I can come over here into where I was and put this image in there. All right, and then we'll go do the other one. We'll do the quantile plot now. And this GGQQ. And again, you start off with your pulse before. That's my variable. Tilde with that first, and then you do the vertical line and smokes. and then data equals pulse. And then again, a title. And we'll go with the resting pulse rate. I'll just say resting pulse rate. Okay. And there's what it looks like. Again, I'm going to go ahead and copy both these over here. And again, both of these look fairly, both of the density plots look fairly bell-shaped. The yes one's a little off of that, a little skewed. But then when I look at the normal quantile plot, the pulse rate for the no's is not as linear as I'd like, but the yeses look very linear. So using those two pieces together, again, we usually look at both of those together. We can now say the populations, the two populations appear to be linear, to be from a normal distribution. Okay. So then our next step is to do the calculations. So let's go ahead and do the calculations. So we'll go back into RStudio for that. And you can use an RMD file if you want. We're going to do it in the console here. T.test. Again, we start off with our quantitative variable, which was pulse before. And then we do tilde and our qualitative variable that we're basing it off of, which was smokes. And then our data is pulse. And then you'd put in the alternative equals. So let's go see what was our question we asked. We go back over here and look at our question, look at our hypotheses. Our HO is that they're not the same. So our alternative is not. So since our alternative is not, we don't need to do the alternative at all. We can leave that off. It assumes it. All right, so I'm going to go ahead and copy this over, and then we can make our conclusion. So here we're in the step of our calculations. And again, this is what we typed into R. It does say it's a Welch's two-sample t-test. That tells you did the right test. So make sure it says that if you're doing a two-sample independent test, you better say this. Again, it's Welch's is because that's the degrees of freedom we calculate. It is saying that we're doing pulse before by smokes. So that make sure this is your variable you wanted and make sure that's the factor you wanted. There's your test statistic. It's negative 0.64. So again, that's saying how many standard deviations below the mean is. Not a whole lot. 0.64 is not that very far. It does give you degrees of freedom. Notice it's not a nice number. It's very strange looking because of the way it's calculated. And then your p-value is 0.52. And then this just tells you alternative hypothesis is that there's a true difference in means of not equal to. So the true difference in means is not equal to 0, which is what we wanted. We don't need the confidence interval this time. All right, so now we can get to our conclusion and our interpretation. Our conclusion is that we're going to fail to reject HO since the p-value is more than the level of significance. And I probably should have summarized these, what they were. I didn't do that in this case, but usually we do that. And then our interpretation is that there is not enough data or evidence to support that smoking affects a person's resting pulse rate. That wasn't exactly what I said in my HA, but that's really what the HA was. That was really my question. And so there's not enough evidence to show it. And there's your hypothesis test. Confidence interval exact same way. Again, we're going to do the exact same thing with whether smoking, and we're going to look to see, is there calculated 95% confidence interval showing how smoking changes the pulse rate over those who don't smoke. So again, you would have, your first step would be to state the variable, the random variable, and the parameter. But we did this. So I'm not going to do it again. Now, if you hadn't done it, you would do it again. So if you hadn't actually just done a hypothesis test on that, you would go and state it right now. But since we didn't, we already did the test, we don't have to. There are no hypothesis tests. There's no hypotheses here. So we're going to go straight to the state and check the assumptions. Again, if you haven't done a hypothesis test, you would do them here. But since we did it, we did this. And so I don't need to do it here. And then we get to our calculations. We pretty much did them already too. I'm going to go back into RStudio and show you that we already did them. We did this. We did a T-dot test, pulse before with factor of smokes, and our data was pulse. We didn't say alternative equal, so it was a not equal to. And it even says 95% confidence interval here. So we actually already had it. We don't need to go calculate it again. We can just go and put in what we already calculated. So we already have those. And again, you can see right here, it tells you a 95% confidence interval. And there's the interval, negative 8.8 to 4.75. The main thing to realize is you can only do this if your true difference in means is not equal to 0. So as long as this was a not equal to, then this is the confidence interval we want. So we can now go to our statistical and real world interpretation. And again, this is that I am 95% confident that the interval, and the interval was negative 8.89, let's say, to 4.75 beats per minute contains the true difference in means, in mean pulse rate between smokers and non-smokers. And I probably should say mean resting pulse rate. And then we can get to our real world interpretation. And this one's a little bit trickier in this case, only because of what we're dealing with here. I've got negatives and positives. So that means that the mean resting pulse rate for smokers, because remember that was what came first. And oh, I meant to tell you why that was. And that is because here we've got our mean group, the no group is first, and the mean group, yes group is second. So R considers the mean group no first and then yes second. So it considers this X1 and X2. That's the only reason we did it this way, is because of that. If you did it the other way, check this statement and see what it is to make sure your conclusions are okay. So you just want to make sure that how you define them is the same way that R will do it. Okay, so the mean pulse rate for smokers is anywhere from 8.9 beats per minute less, because of the negative sign I would say less, to 4.8 beats per minute more because it's positive. Positive means more, negative means less. Then the mean pulse rest pulse rate for non-smokers. Because our interval contains 0, we would say we can't reject HO if we had an HO here because 0 is in there. So you can't really say there's any difference, but it's anywhere from 8.9 beats per minute less to 4.8 beats per minute more because of it spanning the negative and positive. And that's the hypothesis testing confidence interval for 2 sample independent samples.